There we go. Now we should be recording. So,
Huzzah.
yeah, I think at least people know what's going on when I'm not around. So, yeah, I pressed record. I pressed record. We are recording. We're live. Well, that too. So, chapter 5 in phase 2. So let's just take a quick look at what we have after phase 1. So, after phase 1, we have implemented the following. Here's your compiler. It's a pretty thin compiler as it is right now, and it takes in Espresso source, and then it spits out one of two things. It gives you either a okay, or it gives you a not okay. And if we get the okay, it's because the program is syntactically correct. And if we get a thumbs down, well, then the program is not syntactically correct. Okay. Now, what we would like, the green situation to produce a tree. So it's a parse tree, because that serves as a good internal representation for the program, so we can do our semantic analyses. So let's try to do an example, and we can just actually do the one in the book. So let's just do example 5.1. And it has a very simple grammar that looks like this: A, B, or, oh, that's not true. That was an A or B. And a derivation of, should we say, B, A, A, A. Okay, so that's fairly easy. We do A goes to A, A, goes to A, A, A. This is turning Canadian real quick. And B, A, A, A. Is that a leftmost derivation or a rightmost derivation? Just out of curiosity. Rightmost, leftmost, can't tell. Leftmost. Well, you're all right, because it's a leftmost derivation if I always develop the leftmost non-terminal. What's the leftmost non-terminal? It's this one, this one, this one, and this one. What's the rightmost non-terminal? Well, that's this one, this one, this one, and this one as well. So can you please unlock WebEx? Yes. So how do we do that, Alex?
Hit the more and then hit unlock media again.
More?
Yeah.
So yeah, we've done that. And then SMHY, they late. Yes, I'd like to know that too. But I suppose we don't control people's lives. Unfortunately, because then things will be different. Because there, THE apostrophe RE, there. THEY apostrophe RE, they are. Yeah. Oh, okay. Yeah, I guess I'm not up with lingo. Anyways, so let's take a look at this. I could do the following. If I look at my little grammar here, and let me just change colors. Let's say I take the roles and I just write them here like this: A, and A, B. So it would be fairly easy if every time I used this rule, then I arranged these two below the A in some order, and similarly, when I use this rule, I arrange this B underneath this A in some order. So we could get something that looks like this. Should we do it in red? Here's my A at the top, and then I have two things below it, which is the other A and the little a there. So this guy is this one is that one, and this one, of course, is this one. And similarly for this guy here, I get something like this, where that's that, and that's that. And if I use that, then I could now basically completely automate the building of a parse tree, because every new branch is given by the derivation. So if I start out saying, okay, we start with an A. Now that A, because I develop this A into these two, gets to use this rule here. So we get A with two children, A and A. And now this A turns into these two. This guy is the same as that one, so that means we should develop this guy down here. So we get A again. That A stays, but it becomes an A and a little a. And similarly now, that A becomes these two, and these two guys here are those already. So we need A, there's the first little a, little a, little a, and finally we take this A to the B. Oops, I need to write it out again, don't I? A, 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 B. Actually, let me just do something else. Just want to change colors. A, B. So this A, B, of course, is this A, B read backwards. So we can make a actually let's just copy this real quick. So if we copy, this is so much easier to do on an iPad than it is on the board. Because look at this, ha 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 ha, ta-da! Right? Actually, I want to put it there, and then this guy here. I'll just remove it here. Now, if we read, or if we traverse, is actually a better word here. The tree, left to right, depth first, and print all leaf nodes, we get the program, the original. So let me just make a quick copy of that. Copy, paste. So if we put it there, then we can depth first. So we're going down here. We get a B. We come up. Apparently we don't. Hold on. My thingy is acting up. Come down here. We get an A. We get an A. We get an A. So we get B, A, A, A. So, questions. Are all the terminals leaf nodes? Are all leaf nodes terminals? Are all internal nodes non-terminals? Anybody anybody care to say something about that? No? Nobody? You can pick. We don't have to answer all of them. Seems to be true for all trees, of all three. So is that just intuition, or is there anything deeper behind that? Sure. So if I want to be able to do the traversal like I just did, and I only print out leaf nodes, then the leaf nodes better have you better have all the terminals. Yeah, and then so a leaf node has no children, and terminals cannot produce anything else. Why can't I have children of terminals? No, not necessarily. You can certainly have. Oh, I don't know how to say this without giving away the answer that I'm looking for. Um, I think you're right. I just don't think you're saying it entirely. Well, you aren't saying it entirely right, because what kind of grammars are you allowed to have terminals on the left-hand side of? Not context-free ones, right? So context-free grammars can only have non-terminals on the left. So if that's the case, then all the terminals are on the right, and we never replace them because we don't have rules with terminals on the left. So I think that's what you meant, actually. So yeah, that's fine. We'll agree to agree. How's that? So it makes sense that all the terminals gather as leaf nodes, and we can see from that green path that we can read the entire program back off of the parse tree by doing a depth first left to right, a traversal. What are all those A's then, the internal A's? Because what do they tell me? So if I said to you there are 4 non-terminals in the interior of this parse tree, what can you tell me about the derivation then? Nothing. So if you have if I tell you that that the tree, so let's just take this tree here, has 4 internal non-terminal nodes, what can you tell me about the derivation? Well, there are no non-terminals in the program, so be careful with that, because the program consists of terminals. The scanner reads terminals, passes them to the parser, or when requested, gives them to the parser, and then the parser does something with the grammar, right? So don't get confused about having terminals, non-terminals in the program, because you have non-terminals in the grammar, and you can use them in the tree here as well. Daniel says 4 production rules. Again, I think you mean the right thing. So the derivation will take 4 steps to reach the end. Yes, there are 4 terminals in the final product. No, that's just luck here, because we could certainly have had right-hand sides that had more than one non-terminal. Here we're in a situation where every time I replace a non-terminal, I replace it by another non-terminal and one terminal, except for the last step, but I had a non-terminal to start with. So let's see, a derivation will take 4 steps to reach the end. Yep, there are 4 terminals in the final product. No, for production used steps in the derivation. Yes, indeed. There have to be at least 4 terminals, but maybe more. No, that's not true either, because you can have epsilons on the right-hand side, so they can actually just disappear. A non-terminal can become another non-terminal. Yes, it certainly can. What I was looking for here is simply every time I take a step here, then that replaces a non-terminal by something else. And every time we take a step in a derivation, whether it's this one, this one, this one, or this one, we always replace exactly one non-terminal. So for every non-terminal in the parse tree, there has had to been a step in the derivation. So the number of steps, 1, 2, 3, 4, if that's how we count them, or 1, 2, 3, 4, 5, if we want to count sentential forms. So it's specific to whatever grammar you're using. So should we just answer these questions? Are all the terminals leaf nodes? Yes. Are all the leaf nodes terminals? Yes, because we have a CFG, right? Are all the internal nodes non-terminals? Yes. Well, lucky us, we got it right. So let's do one more example before I'm actually going to get you to just read this thing yourself, because there's nothing complicated in it. It's just stuff that needs to be said. What we do have to do is yeah, sure. Then let me know when you're done. Then I can just talk about something that we have to do later on. So in section 5.5, you don't have to read that yet. So just read up to 5.2 and including 5.4. And if you want to, you can read that 5.6 about. Okay. So you can read 5.6 if you care to see the example for the little language. 5.2 is just something that's nice to know, and it really is just something you should understand already from your 326 book. So that's just a recap, and the rest we've already done now. So let's just try another example here real quick. So can we just say something here like in general, for a rule, A goes to alpha, B, C. No, that was not an alpha, that was an A. We get a parse, actually a partial parse tree. That looks like an A at the top, that's the left-hand side. So this is the left-hand side, and then we get A, B, C. That's the right-hand side, and at some point, this B becomes something, right? So that depends on all, but so this here is the derivation. So the tree of the derivation of B. Okay. So let's try another example here, just real quick. And it looks like E goes to E plus T. Actually, can we try something? No, that's fine. We'll come back to that. Or T. T goes to T. I was just about to make something up there, but I resisted. Yeah. And this is the simple version. We'll work with this grammar later on. And let's do a the leftmost derivation of ID plus ID multiplied by ID. Okay. Well, that should be fairly easy. And in general, remember, if it doesn't say what the start symbol is, it's always just the first defined non-terminal. So we'll start with E. And then the question is, what do we do? So we're doing a leftmost. And we got to figure out whether we should take E plus T or we should take T. Let's see. We should take E plus T. Right? Because we need the plus first, and then we'll let this E become an ID, and the T will become the multiplication. And we're doing leftmost derivation, so we have to develop this guy. We did that one. Next step here is the E becomes a T. Just checking to see if I'm getting it right. Leftmost, that's this T. And then that T becomes an F. There's an open mic here, so unless you want to tell jokes. Right, so that F then becomes an ID. And we still have a T. And now you can, I'm sure you could do this, plus T times F. Oh, I was hoping I could fit this onto one line, but that's not going to happen. And we get ID plus F times F. That F becomes an ID. ID plus ID multiplied by F. And I think we're done now. ID plus ID multiplied by ID. We took that one, and then we're done. So if I want to draw the parse tree, let me see if I can actually fit it over here. Actually, hold on. I know what I'm going to do. I'm going to take this, move it a little bit. Take this, move it down here. Oh, I love this iPad stuff when it works because it's just cool. There we go. So now we have room to do a parse tree. Should we do it in green? Right. So it's really just follow the derivation. So we start with an E. That E becomes E plus T. And that E becomes a T, which becomes an F, which becomes an ID. This T becomes a T and an F, and they are multiplied, and this F became an ID, that T became an F, and then an ID. Now, if you look at this, you'd probably say, why do I need all those temporary steps? So you could sort of say, well, you know, this stuff here, and this stuff here, and maybe even this stuff here, why do I care about that? Couldn't I just represent it in the following way? So, or maybe we'll just say plus ID multiply ID and ID. So wouldn't you say that this is better? Well, so to prevent ambiguity and force order of operation, I hate to say it, but no, because the reason that that's not the case is ambiguity. Ambiguity you should not have in your grammar. And since the derivation is what drives the building of the parse tree, if your derivation works with an ambiguous grammar, then we have a problem. So we don't want ambiguous grammars. Order of operation must also be defined by the grammar, which means that when you have a derivation, then the order is given simply by the way that things are done in the grammar. And since we haven't seen that, you couldn't possibly know that, but once we've seen that, I'm sure you will agree with me. Well, it's true, so you'll kind of have to. Yeah, I don't actually know why, you know, why do I care? Why do I care here that an E becomes a T becomes an F? I really just care about the fact that I have a plus with an identifier on one side and on something on the other side here, which is a multiplication of an identifier and an identifier. Oh, and just real quick, if you look at this grammar here, you can see that the order of operation is maintained here, right? If you want to add a whole bunch of things together, basically you're getting a bunch of e's, or you're getting a bunch of t's added together because you keep recursing on this e thing here, right? And each of those e's eventually become a t, and a t can be something that gets multiplied together. So if you think about the way that the parse tree is built, your multiplications will always be further below the pluses. And if you look at this, when you have a t, that t is something that gets multiplied. That t will never have an e below it, right? Because you have to have the e's at the top level, which then becomes t's, and then the t's become f's. We'll come back and talk about that much more next week. Right. So, if you don't mind, I'm going to propose something a little bit better than this. Something that's actually a little closer to what we're going to do in the assignment. Or perhaps even better. Now, what's the problem with the green stuff? Is that a plus or lowercase t at the top? That's a plus. So this guy here, that's the plus operator. That green parse tree there is very precise. It says, I want to add something together. So I want to add something together, which is this part and this part. This part here goes there, and this part goes here. So that's just an identifier. And here I want to multiply something together with the ID there and there. So I get this. And then I can take away these brackets, and I get what I originally had. So what I'm really doing is I'm using that plus operator to say, hey, I have a binary expression, and I'm using the multiplication operator to say I've got a binary expression. Maybe it would be better if we did something like this. Binary expression plus identifier, binary expression, multiply, identifier, identifier. Because now you have everything is what postfix. No, it's not postfix at all. It's correct precedence of operators, because you got to multiply before you add, and because you have to multiply before you add, these guys are tighter bound together than the entire thing. So it's a sum of this and this. If I wanted to make this postfix, I certainly could, because we could just so as an aside here, if we want to translate to postfix, then visit left, visit right, print. All right, so visit left, we're here, visit left, we are there, visit left, it doesn't have any left, it doesn't have any right, so we need to print it. All right, we can do that, so that's an ID. We come back here, visit right, visit left, that doesn't have any left, that doesn't have any right, so print that. So we get another ID. We're still here, we come back up here, do the right one, no left, no right, print the ID, that's an ID. Now we're back up here. Well, we've done the left, we've done the right, so we need to print that. Multiply. Now we're back up here. We've done the left, we've done the right, so print that, and we get that. Okay. Right. So I think this is a better way of doing it, because now we can sort of standardize things, and we can actually make a class. So we could do something where we say class bin exper something 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 bin exper, and then we have to have something which is the left, something which is the right, and operator op something something something, some other stuff down here. So we sort of get a nice idea of how we could actually build parse tree nodes in an object-oriented language, and basically we can now just go through our grammar and say, what sort of parse trees do I need? And in general, if you have a grammar, you would have many more rules than you have parse tree nodes. So let's just do something here. Let's go to the compiler project and let's see if we can find the grammar down here. And I want to I really want to make this a little smaller if I could figure out how to do that. Is it shift minus? Shift something minus? No. Alex, do you know how to make this smaller?
The PDF?
Yeah.
Or even through Chrome, or... Oh, yeah, you are in Chrome. Is there a menu button somewhere?
There's not a whole lot of anything.
It's not a whole lot of anything. Oh, wait, yeah, scroll up to that and then hit... Oh, well. That's a good question.
Oh, well, never mind. I'm pinching and then that happens.
Goes to tab view.
That's fine. We can use this thing here.
Control minus.
And now I'm just going to see if I can take a picture. How do I take a picture? Like that. And we'll take this and we will say copy. And then the vain hope that we can insert it here. Hey, look at that. It worked. Now, take a look at all these guys here, right? Right, so this is called an equality expression. This is called an AND expression, an exclusive OR expression, an inclusive OR, a conditional AND, a conditional OR, a conditional expression, and etc., etc. Actually, can I just paste that again? Apparently not. I guess we can insert it again. Here we go. I just wanted a little bit of space down here. And if I just scribble here, this instance of that's an operator. This equal and this not equal is an operator. This and is an operator. This whatever it is an operator. That's an operator. That's an operator. That's an operator. And all of these are binary operators, right? So we could have done something where we say so what about a rule that says binary expression colon equal some expression and then some operator, which could be instance of or equal or not equal or etc., followed by an expression. Now if I did that, well actually, so why don't I just have one big rule where I say I've got something on the left, I've got something on the right, and then I pick an operator in the middle? Anybody have any idea why I've got them laid out like this? And if you go back to here, you can see there's an entire page before where there's plus, minus, division, multiplication, mod, all the shift operators, and all the relational operators as well. So actually, let's just do here. Let's do an aside example, if you can do that. Aside example. E goes to E plus E or E minus, multiplied by E or ID. Okay, and then now I'm going to ask a derivation for ID plus ID multiplied by ID. Looks ambiguous. Yes, it does. Now, you might say, oh, well, you know, this is not like you had before. That's true. So can we make it the way that I had it before? Yes, we can do that. We'll put a T there, and a T there, and a T there, and a T there goes to ID. Or actually, should we make it an F? Just 'cause that's what we had before. So if I do this, and we'll just do this real quick, I could do something where I say E goes to E plus T, goes to T plus T, goes to ID plus E times, oops, those were F's, sorry, times F, goes to ID plus F times F, goes to ID plus ID times F. This is totally autopilot. Yeah, and the corresponding parse tree, I'm going to do the quick version here. Else we could be drawing till we're blue in the face. We'll just move that over a little bit and change the blue. Or what if I did this? E goes to E multiplied by F, goes to E plus F multiplied by F, goes to F plus F times F, goes to ID plus F times F, goes to ID plus ID multiplied by F, goes to ID plus ID multiplied by ID. And if I did this right, let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Yep, so we do a parse tree for it as well. Well, it's a multiply on an ID. No, it's not. So multiply on a plus, on an ID, on an ID, on an ID. So look at that. I got two different parse tree nodes, and it's not because I did a leftmost derivation in one and a rightmost derivation in the other. This is a leftmost derivation, and so is this. So as Mark said, it's because it's ambiguous, and yes, that's true as well. But also, I've got some problems with my operators, because obviously this is not the same as that, right? This is an ID plus some virtual brackets around ID multiplied by ID, because they represent that part. Whereas over here I have ID plus ID, the virtual brackets around that, because they represent this, multiplied by ID, and that certainly isn't the same. So what we do is we have some techniques, and we'll talk about that next week, where we can sort of cascade the grammar into a whole bunch of different rules, one rule per precedence level, and that's why we do it this way. But once I've built the parse tree, I don't really care whether it was well, from the parse tree point of view, whether it's an equality expression, an AND expression, an inclusive or whatever, because they all look the same. They have an expression on the left, an expression on the right, and some operator in the middle. So these can all be represented by, well, so actually, let me rephrase that. I want to say all the rules with a binary operator can share a class. So for example, C source AST binary expert, which I'd like to show you now. So when you get this this handout, you will notice, if I can actually find my way to where I want to go. Source, you'll notice that in your AST directory, you now have a whole bunch of different parse tree nodes. And let's just look at that binary expression. That didn't work. There we go. So the most important thing here is actually I'm going to take a picture of it, open it, and say copy, and then I'm going to go back here and insert that. And now the stupid thing stopped working again. Sorry, the pen is not working. There we go. Right. So if you look at this, then we can cross this stuff out here, and we can cross this stuff out here, because that's not something we need to talk about right now. Really, what's the most important part is this stuff up here. If we look here, that's the superclass of this thing, and now you might say, well, what sort of a class hierarchy might you want to have? Well, the class hierarchy we have looks something like this, just from memory. AST is the sort of general syntax tree node, abstract syntax tree. Below that we have expression and statement. And below that, a whole bunch of different expressions and a whole bunch of different statements. So there's binary expression, unary stuff, statements. There's for stat, do stat, etc. These two guys, as well as this one here, are abstract, and you remember an abstract class is something that you can't instantiate. So we have a class called binary expression that extends expression, and then what we can see here, these three things, these are the children, and they also happen to correspond to the right-hand sides. So if I go and look at all these things here that we said were binary expressions, look, one side, 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 one side. So they all have two sides here, right? Now somebody might say, well, wait a minute, what about your second rule here? This guy, this guy, this guy, and this guy. But that's fine, because this exclusive OR expression is just this guy up here, which is this. Or that, but that is just this, which is that, or this, but that is this or that, and so on and so forth. So we end up, if I have a binary expression, we end up with two things, right? One on the left and one on the right. So those are the ones we have here, the left and the right, and we just say that those are expressions in general, because we don't know what kind of expressions. They could be complicated binary expressions, they could be a simple use of a variable, or they could be a negation of a number, who knows. And then we've just created a class called binup for all the binary operators. So these guys here are just binary operators. What we do, then we just we set a couple of variables here. This one and this one are in AST, so we've inherited those from AST through expression, and the rule for this is that we're going to fill in this children array. So these are all the the children, so those guys. We're going to fill that in, and you can see we do that here with left, right, up. And we set this thing, we set this n children there just to be the length of this array right here. And then we've added here, these guys here are just accessors, right? So we can now go through our grammar and figure out for each rule what sort of parse tree nodes do I need to create. Then I can go and I can build parse tree nodes based on this example that I showed you here. Basically it's figure out if it extends AST directly. If it's an expression or a statement, then it extends those instead. Create a constructor that takes in all the children. Call the constructor of the superclass, set n children, fill in the children's array, and provide some accessors that return the appropriate thing, and find some good names for them so that you can use them later. So if I say to you, go and do that, then somebody would probably find me and run me over, because this is an extremely tedious thing to do, which is why I've done it for you. So I've done all of these, and we can take a quick look at AST, and you can see up here we have there's the n children, and there's the children array. Somebody really ought to put some comments in this file, Ben, or me, or Alex, or somebody, except for the other Ben. He's got no race and no chicken in this race. Nope. And then we have a bunch of constructors, and the constructors can take in either another AST, just a token, or just information about what line and column we're in. And this is just so we can get the column and line numbers set correctly. I can turn it to a string, which does absolutely nothing because AST is not in itself a parse tree node that appears in the tree. And if I look at expression, we'll see that extends AST, and it just implements a bunch of constructors that just pass on the token or the AST to the AST class, and that's it for that. So not super complicated. The most complicated thing is, what are all these things here, right? I mean, some of them are pretty obvious. Let me just try to see if I can do the following. I'm going to take a picture of that. I don't know if that worked. And then say save. That's not what I wanted. We'll copy that, and then we'll go here. Oops, that's not what I wanted either. All right. What I really want is I want to do this. Copy. Okay, never mind.
Yeah, I don't think you can slice an image like that.
Well, we'll do it like this then. We'll put that here, and then we just need to do the, let's see, how far did we get there? We got down to new. All right, so that's fine. Here I should be able to go down to, I can actually do it here. There we go. Now I really should redo it, shouldn't I? I need to get a new pen because this is getting to be stupid. Yeah, we'll stick with this. Okay, so if I look at some, am I cutting in and out? I'm sat right here all quietly.
I've been hearing him fine. Maybe your end.
Alex says it's on your end. That's of course the typical tech support approach to things. What do you mean we didn't do anything wrong? It must
Works
be your
on my
end.
machine.
That's right. So Ryan, can we take that question in a second? The Apple Pencil tip. Yeah, but this thing is brand new, right? I mean, how often does one need to do that? Suppose I could try getting some new ones of those. Oh, well, anyways. So if we look at these and we know nothing about anything, then we can probably fairly easily figure out what is, right? So if I look at this and we say, all right, this thing here is probably for something, something, something. That's probably if something, something, something. An invocation, that's probably f of something. A do is probably do something, something, something. A continue stat is probably just the word continue. A class declaration is probably just class a curly bracket something, something, something. Break stat, well, that's just a word. Break. A block, well, that's just a set of curly brackets. Binary expression, that's something, 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 some operator, something, something, something. The bin up, well, that was the plus or the minus or the any of those. An assignment, that's something, something, something equals something, something, something. An array access, that's something, 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 square bracket, something, something, something. So if we look at these for a little while, these for a little while, some of them become fairly obvious. And what we got to do, well, let's just do a few over here. While, that's just while something, something, something. Unary post expression, that's something, something, something plus plus, or something, something, something minus minus. Unary pre is plus plus something, or minus minus something, or plus something, or minus something. This, that's the keyword. This switch statement, that's some switch stuff. Super, keyword super. Static init is an invocation of this. No, it's not. Static initializer is the word. Static something. I want to come back to this one in just a second. More on the next page. Return stat, the keyword return. This sequence thing here, I want to talk about that as well, and so on and so forth. So we need to match each rule in the grammar by one of those. Now I wonder if we can just go back to here, and I can just rope this thing here real quick and say copy, and then we can go back over here and just paste it in. Yeah, that works, right? So this guy and this guy, they have to create new binary expressions. That one as well. This one, that one, that one, that one, that one. So we could type our non-terminals right now. All non-terminals are typed, not tied, typed as AST, and that's because we're not building any parse trees right now. So we just got to give it something. They need now retyping to what we actually create. So in the situation where I have equal, equal, and not equal, I'm going to create a new binary expression with those things. And in the case of the relational expression, in case of the relational expression, I probably get something that is already a binary expression of some sort. So what we need to do is we need to figure out what is the what's the thing on the left hand side going to be. So what's the type of the non-terminal going to be? And then you might hear say, oh well, this is super easy, right? Because that's a binary expression, that's a binary expression, that comes from above, that's a binary expression as well. So this guy here should be a binary expression. Well, let's just take a quick look at the grammar before we do something stupid. So I have a no way of highlighting this. Well, yeah, we have the equality expression here, which is a relational expression. Relational expression can be a shift expression. Shift can be an additive. Additive can be multiplicative, and a multiplicative can be a unary. So now we actually have a problem with this rule up here at the top, and I'm just going to pick this one out and talk about that for a second. Copy. Paste. Put it there. Oops. Make it a little bigger. You all would agree that this probably should say something like new binary expression. It takes in three things, and this multiplicative expression should go, or the parse tree of that goes there. The parse tree of that goes here. And here goes a new bin up for that. So this and this are all binary expressions. What's that? Well, that's not a binary expression. It says in black on white that it's a unary expression. So now I get in a little bit in trouble if I want to say that this thing over here is a unary expression, because it's not. I also get in trouble if I say this thing here is a binary expression, because it's not. It's a binary expression if I pick those three, but if I pick that one, it's a unary expression. All right, can we find a type in my parse tree node hierarchy that can hold both references to unary expressions and binary expressions? Expression, yes, exactly. Good. So we should type this as expression. So we get non-terminal expression, multiplicative expression at the non-terminal section of the cup file. And if I want to type it in the way that we should have it in the cup file, then let's just let's take a look at the cup file and there. Not CD, Control A, DD, Emacs. And if I search for multiplicative expression, you can see right here that my multiplicative expression has a non-terminal type expression. Let's go find it down. Oh, I didn't spell it right. Multiplicative expression. So there it is. And I'm going to take a picture of that. Open that picture. Just focus in on that. There we go. Copy that. I'm starting to not like this technology anymore. Here we go. So this is the cup rule. I've added some stuff to this file. So when you get it, I put this stuff up here, which is just a comment. I haven't filled it in. I've just said type colon. I strongly suggest that you fill it in because it is extremely useful to know what type it is. This sort of stuff is called action, and action is Java code that builds the parse tree. And it always looks like this. And then in here goes some Java. And the result should be put in result. So if you look down here, for example, we can see that there's the action stuff. Result equals, I create a new binary expression and I give it something, something, and something. Here's this new binary operator. O is just the token, then so we can get some line information. And it's a binary bin op, and it has a whole bunch of different types. And here we use the mod one because this was the mod guy. Remember when I said here that it's the parse tree of the left-hand side there of the binary operation, and it's the parse tree of the right-hand side that goes there. How do I get those parse trees? Well, I can name these. You can see that I've given them names by saying colon something. That means that when I go and run the rule, or when I derive the rule for here, for example, for this multiplicative expression, that rule at some point assigns something to result, because that's how you build the parse tree. Whatever was assigned to the result variable for this rule, if this rule is ever run, is placed into E. So this and this are, actually they're not partial, they're sub-parse trees. Sub-parse trees. So that makes sense, right? Because when I create a new binary expression, then I get a binary expression with 3 children. This is the E1 child, that's the E2 child, and that's the bin op that I create right here. And of course, what I can do now, I can lift some information out of my my parse tree nodes, because if I were to open this binary expression, I'd be able to see what are the types for the first 2 guys here. So let's just try to do that real quick. Control XC, more binary expression. So look there at the top in the constructor, it says that both left and right are of type expression. We kind of already knew that, right? But what I get from that is that both unary expression and multiplicative expression should be of type expression. Well, we already know that this is type expression, but that's now given me the type of this guy here. So we can use the types in the constructors to determine the non-terminal types that correspond to it. Now I want to say some more. I want to talk about static initializers, and I want to talk about sequences. And I think I'm just going to do sequences here real quick. So the sequence is a special node to hold lists of any length. So for example, if I have a rule that says A goes to A, or B, then that language is B, BA, BAA, etc. So that's any length of terminals, right? And we can use a sequence in a situation like that. Like, for example, if you think about the number of parameters given to an invocation, that has to be of type sequence because we don't know how many we have. And it's always going to be in a situation where I have a recursive call on myself like this. So a sequence, is there an open mic? There is an open mic. Not anymore. Maybe there is still. Is that it? Yeah. So a sequence, you create it with one element. I can't type it all here now. One element. And you append further elements. So if we had A goes to A or B, then the action would look something like, if I could actually spell out this nicely. This always happens when you are in a hurry. Result equals new, I don't know, X, and we'll give it a name B. We'll take a B in. And in this situation up here, we would get something here. We'll call that AA, and we'll call that A. Then we just want to call append to get A appended to that. There is a merge for merging sequences, and we need to use that, I think, about 5 times. We'll talk about that next time. So let's see, Ryan had a question that said, quick question, when we copy the grammar rules into the cup file, do we remove the apostrophe symbols? Well, yes, you replace the apostrophe thing. The things in apostrophes are terminals. Terminals in the cup file are represented by tokens, by the names that you give the tokens, and that is what comes from the token section of your cup file. That's all those names you used at the very top, which you got from the token array. So import becomes import all the way through. The semicolon becomes SEMICOLON, all capitals, and so on and so forth. Yes, indeed. Anything else, or shall we rush on to something else? Because I got another one coming up in a second. So, unless there are any other questions, remember, due by midnight. If you're late, too bad. Phase 2 will be open after midnight. No, I can't open it until everybody's handed in, because Phase 2 has the solution for Phase 1. Can we go back to the productions like 3 pages ago? Here? Further? Here? Here? Yes. That doesn't work, you're right. So let me fix this real quick. The easiest way to fix this is to do the following. We'll put an ID there. Turn that into an E, turn that into an E. Erase that. Let's see if we can fix this up. E, E, E. It's easy to turn E's, F's into E's. No problem here. How's that? That's better, right? All right. Yeah. No. Thanks for catching that one. I didn't see that. That's what happens when you're trying to make things up as you go along. All right. End of story. I will see you. So, by the way, tomorrow, office hours at I think maybe I'll start around 3 o'clock. I will try to do something on WebEx here. We will try to write a small script to do some testing of the compiler. So welcome to Bash Hell tomorrow at 3-ish. All right. Now stop recording is what you want to tell me. So that means I gotta go here. I'll see you guys later. Bye.